Higher Notes, Unit 1, Section 4, Collisions and Explosions. This is part 4, Impulse. So what's this about? Well, let's introduce this idea of impulse, by imagining a golf shot. So let's imagine we've got like a driver which is going to be hitting a golf ball. So there's the golf ball there. And the driver is being swung in like this. That's clearly at some speed. And it whacks into the golf ball. And of course the golf ball goes flying off. Now in this scenario, we're not going to be worried too much about the angle of launch or anything like that. So we're not going to get into projectiles. What we're interested in is not so much the before the collision, because this is a kind of collision, it's two bodies colliding, not the after of the collision, but the during. Okay, so the during of the collision is really our main sort of focus here. Now, interestingly, what happens sort of during the collision something slightly kind of strange actually happens to the ball. So we're going to focus in on the golf ball as opposed to the club. Okay, the golf ball is our object of interest. There it is there, okay. Well, interestingly, if the golf ball starts off sort of like this, then I'm going to exaggerate this, right, but when the club makes contact, the golf ball gets compressed and it kind of gets squashed, sort of like that, and then it decompresses back to its original shape again. So this is the compression or squashing, if you like, and then you've got decompression where it stretches back out to its normal size. So this is no contact, normal shape, if you like. Okay. So what you've got to imagine then is that as the club makes contact, just before the club makes contact, the ball is its normal shape. As the club presses in on the ball, it gets more and more compressed. And the force on the ball is going from 0 up to some maximum there. So at this point we're going from sort of 0 force to maximum force. Okay. Once you reach maximum force, the ball starts decompressing, and we're going in the second diagram from maximum force to 0 force. So the point I'm trying to make here is that during the contact of the club with the ball, the force on the ball is not constant. It rises from nothing up to some maximum, and that's the compression stage, and then it goes from that maximum back down to 0 again when the ball leaves the club, and no force is there. Okay, so bear that in mind as we're doing this analysis of the ball. So the body of interest here is the golf ball. Well, let's draw a free body diagram. If you were the golf ball, what would you feel? You would simply feel a force acting on you. Your mass is m, and taking you from rest up to some exit speed, which will be quite fast, probably for a golf ball. And because the force is varying, so it's kind of going from nothing up to some maximum during the compression, and then it's kind of going from that maximum back down to zero when contact's lost during the decompression, we need to have the average force rather than just the force. Okay, so it's really important that you realize we're dealing with the average force on the ball, F bar. And that's going to be an unbalanced force. So we apply Newton's second law, and what do we get? Well, we get that F equals ma. The ball obviously accelerates from rest. I'm just going to put in the bar here though, because as I've discussed, the force is changing, so we need an average force. Well, let's just unpack that a little bit. Acceleration is v minus u over t. That's just the standard acceleration equation. Now I'm going to write this slightly differently from normal. I'm going to call v minus u, the change in velocity of the ball, delta v. That's the Greek letter delta. It looks like a little triangle. That just means change in velocity. And for symmetry, I'm going to call the time of contact delta t. Okay, that's the time of contact. And all I'm going to do now then is bring that delta t round to the left-hand side of the equation, and I'm left with m delta v on the right. And that's me got a very useful equation now. What do I have? Well, on the right hand side, I've got m delta v. M, mass times velocity, remember, is momentum. So m delta v is the mass times the change in velocity. That's effectively the change in momentum of the ball. And that, of course, will be in kilograms meters per second. So that's the change in momentum of the ball. And on the left-hand side, this product of the average force F bar and delta t, the duration of the contact, is given a special name. It's called impulse. And looking at the units of impulse, it has to be Newton seconds. Now be careful with that. It's not newtons per second, it's newtons time seconds, or Newton seconds. In words, we could therefore write that impulse equals the change in momentum of the body. They're numerically equivalent. They've got different units, but numerically they will always be identical. Okay, let's do a little example then. So, example, a golf ball is struck and leaves the club at 40 meters per second. it is initially at rest and has a mass of 0.2 kilograms. If the club is in contact for 0.04 seconds, find the force, that's the average force, exerted by the club on the ball. Okay, so the golf, that should say golf ball, is struck and leaves the club at 40 meters per second. It is initially at rest and has a mass of 0.2 kilograms. If the club is in contact for 0.04 seconds, find the average force exerted by the club on the ball. Notice the time of interaction there, 0.04 seconds, is quite small. In these impulse problems, the interaction time is always very, very small. That's one of their features. Right, solution. Well, list your variables. F bar is our unknown. M, 0.2 kilograms. U is at rest. V is its final velocity. It comes off at 40. You can see the delta V is just going to be 40 minus 0 there. And the delta T, the time of interaction, 0.04 seconds. Well, right away, you can see that delta V is just 40 minus 0, which is 40 meters per second. So, set up our equation. F bar delta T is m delta V. Put in our numbers. F bar times 0.04 equals 0.2 times 40. Don't do any calculations till the final line to avoid intermediate rounding. So 0.2 times 40 divided by 0.04. What does that give us? Well, let's check. 0.2 times 40 divided by 0.04, and you get that the average force was 200 newtons. Okay, that would be in the direction of travel of the ball. Okay, so there is the average force, 200 newtons. Now you need to be familiar with how that gets plotted on a graph. So let's sketch how that force would typically vary on a graph with the golf ball, like so. So we're going to plot force in newtons there and time in seconds there. I'm plotting my time in seconds. Be on the lookout for impulse problems where the time might be in milliseconds. I could have plotted it in milliseconds, it would be 40 milliseconds. Just be on the lookout for that. Well, we hit a max, our average force, I should say, is going to be 200 newtons. Okay. Now, because of the way we do these problems, we're going to assume that the force varies in a nice uniform way. What do I mean by that? Well, the whole interaction takes 0.04 seconds, so let's put that in. And if we go to the halfway point, which would be 0.02, you'll find that the maximum force is reached halfway through the interaction, so about there. So let's put that with a dot there. Notice I've not written any values on the force axis yet. So here's how it would go. This is how we're assuming the force varies during the interaction. Starts off at 0 and builds up to some maximum. But the build-up and the decrease are assumed to be nice and uniform and linear. Well, that F max, which is here, would have to be 400 newtons. Why so? Well, if the average F bar is 200, because it's a linear graph, that will always be half whatever F max is. Now I know this is 200, so that's how I worked out that the max was 400. Okay. So F bar is half of F max. That's the case for all linear type graphs like this. So there is the graph of our motion. Now, an interesting feature of these graphs is the area under the graph. This shaded area here. Well, why is that important? Because if you look at the area under the graph, it's the area of a triangle, so it's half times the base times the height. Okay, let's work out what that actually is. Well, it's a half. Now the base is actually the delta t. It's the 0.04 seconds. There it is there. Okay, and the height, well, the total height of that triangle is F max, not F bar. Oh no, F max. Now, a little bit of tidying up of that. Well, the half of F max, you can look at the way this is working out here. That half, if we multiply it onto the F max, well, the half of F max, as you can see here, is F bar. So what we've actually got here is F bar times delta t, which of course is the impulse. Moral of the story: the area under a force time graph always equals the impulse. Okay, and that of course would have units Newton seconds. Now remember, impulse equals change in momentum, so if you get the impulse from that area. You've got the impulse in Newton seconds. That's numerically equivalent to the change in momentum. So sometimes you get at the change in momentum by looking to get the impulse. So finally, you often get problems where it says something like the golf ball is replaced by a sponge ball. How would the graph sort of be different? Well, the thing about using a sponge ball is that it's basically going to give you a longer sort of interaction time. So you get a graph like this. There's a longer compression and there's a longer decompression. So the graph would be something like this, where the delta t is bigger and the maximum force experienced is less. So something a wee bit like that. So this would be a sort of sponge ball. You can see it's got a greater delta t. The softer material keeps the club in contact for longer, and it basically decompresses much more slowly. So you get a longer compression and a longer decompression. And just before we leave this graph, here is the compression of the ball, where the force goes from 0 to F max. And here is the decompression. And you may in class have seen film of a golf ball being compressed and decompressed. And that compression is longer for the sponge ball, and the decompression is also longer. So because the delta t is bigger, if we assume that the change in momentum for the sponge ball is the same as the change in momentum for the ordinary ball, and that's often the scenario, to keep the area under the graph the same, that's the impulse, we need a lower graph but a wider one, so it's lower and wider to give you the equivalent change of momentum, i.e. the equivalent impulse. And that brings us to the end of the impulse.